Hello students, welcome back to PH107 Quantum Physics and Applications. Today I'm going to continue our discussions on Heisenberg uncertainty relation, and then I will discuss about statistics of distribution and try to establish a connection between distribution and Heisenberg uncertainty relation. But before that, let's recap what we have learned in the previous lecture. So the complete set of uncertainty relations are delta x, delta px is greater than or equal to h cross over 2. So uncertainty relations imposes an upper bound in the simultaneous measurement of a position and momentum of a particle. And similarly, we can write down the uncertainty relation for energy time canonical conjugate pair. So delta E times delta T is greater than or equal to h cross by 2. So what it means that it is impossible to carry out any experimental measurement that allows the position and momentum of a particle to be simultaneously measured with an accuracy that violates the uncertainty principle. So it means that you cannot measure the position and momentum of a particle with an accuracy which is established at the upper threshold of the accuracy is set by the uncertainty principle. So this product cannot be smaller than h cross over 2. This is the meaning. Okay. So this uncertainty in the measurement do not arise from the limitation of a practical measuring instruments, rather from the need to use a large number of wave numbers to represent the matter wave packet localized in a spatial in a small region. Okay. So how to verify this relation holds in general in a very simple way. So Heisenberg himself came an idea of a microscope measurement. So what he said that, okay, so he designed a thought experiment by which he showed that if you want to measure the position and momentum of a particle simultaneously, the measurement or the precision of the measurement or the precision of the values measured for the position and momentum cannot violate this uncertainty relation. So let's see what he has proposed. So this is known as Heisenberg microscope. This is a thought experiment, and what he has said, okay, let's measure the position and momentum of a particle. So here is an electron which is at rest. You shine a light. When the light is scattered from this electron, you measure this scattered light by a microscope. Okay, and when this photon interacts with this electron, this also imparts some momentum to this electron, and then this electron becomes a recoiling electron, and this scattered photon goes along the direction of the microscope. Similar concept you have seen in the case of Compton effect. Okay, so that is the idea, that you shine a light and you collect the scattered light on the microscope, and by which you try to measure the position and momentum of this particle electron. Okay, so here is another concept that you have learned that we are going to employ here. So if you would like to apply or get a minimum uncertainty in position, then you need to use a shorter and shorter wavelength. Okay, so what it means that if you recall the X-ray diffraction discussion, in which you have a crystal planes. These crystal planes were separated by a distance d, and there were atoms which are situated at a certain distance. And if you want to measure the distance between the two atoms or distance between the two lattice planes, then you need to use the light with wavelength which is shorter than either the distance between the two atoms or the distance between the two lattice plane spacing, which is d, or which was d. And that's why we use X-ray, because X-ray wavelength is comparable or is smaller than the lattice spacing, and that's how we were able to resolve the crystal structure of, let's say, the nickel crystal. Okay, so the same holds here. So to determine the position of a particle accurately, it is necessary to use light of short wavelength. But if you use the short wavelength light, and by this relation, it means that the energy of this light is more and more. So it means that a photon of short wavelength has large energy, which implies that energy is directly proportional to the momentum. So it means that if your light has large energy, so it will also impart a large momentum to this particle. Okay, so it will give a large kick to the electron, so that it's to make the momentum uncertain. On the other hand, to determine the momentum accurately, electron must only be given a small kick, so that its momentum does not go to the fuzzies. It has to be precise. Now it contradicts the two things. This means that using light of long wavelength, you can make sure that it's going to impart a very small momentum kick, or a very small kick to the particle. But if you start using a log length of the light, it means that your position become uncertain. Okay, so here is a schematic of this thought experiment, or what we call as a Gedanken experiment, suggested by Heisenberg himself. So here is your electron at rest. This is light coming with momentum p naught, wavelength lambda naught, and when it is scattered, this lens collect all the scattered light, and then it will refract, and this screen collects all the diffracted light, and then you will see a diffraction signal here in the detector, which has a central maxima, which looks like this. Okay, so what it happened, that a single photon is scattered from an electron, which is collected by the lens and diffracted onto the screen behind the lens. Now the lens has certain aperture, which is going to collect all the scattered photon, and the angle between this electron and this aperture along this normal is theta. So if the scattered photon is to be collected by the lens, it has to be scattered within this angular region or angular range plus minus theta, which is shown in this particular figure. Okay, so now when this light is scattered from this electron, it will impart some momentum, and because your light is coming along this direction, and this is your angle theta, so we can calculate what is the momentum, or the component of momentum, that has been imparted to this electron. So it is easy that this is your h lambda naught, or this is your h lambda, this is the scattered photon, this is the angle theta. So the imparted momentum on the electron is plus minus h over lambda times sine theta. So you take the component along the direction of this electron. Okay, so once you have this momentum that has been imparted to the electron, so it is easy to know what is the uncertainty in momentum. So the uncertainty in momentum is given by 2h divided by lambda times sine theta. Okay, now the photon is collected by the lens. This scattered photons is collected by the lens, which has been diffracted on this screen. Okay, which forms this image of your diffraction signal. Okay, so the spread, this spread of your diffraction's central maxima represent the uncertainty in the position of the electron, and by using the physical optics, it is straightforward to calculate what is the uncertainty in the position of an electron, which is given by delta x is equal to h over 2 sine theta. This you have seen in your 10 plus 2 standard. So now we know what is delta x, we have seen what is delta px. Let's multiply both. So what you will get h. So it means that the uncertainty in measuring the position and uncertainty in measuring the momentum of an electron is not a random, or you cannot go perfectly precise way, but it has a value h. So it means that it fulfills, this h is larger than this h cross over uh, uh, 2. Okay, so it means that it satisfies the uncertainty principle. Okay, where h cross is your h by 2 pi, so this quantity is your h over 4 pi, which is smaller than this quantity h what you have got. So it means that Heisenberg has demonstrated by coming up with this thought experiment, that by whatever way you try to measure the position and momentum of an electron simultaneously, it has to satisfy uncertainty relation. It cannot violate uncertainty relation. Okay, so now let's come to statistics of the distribution and how this concept is related to the uncertainty, and how the uh, measurement of any statistical distribution and the uncertainty is going to follow this uncertainty relation. Okay, so here is a understanding that the uncertainty relation is necessarily associated with some kind of distribution. So if, let's say if we measure a particular physical property of a particle, maybe momentum, maybe position, we get different value each time. So if you measure once, second time, third time, fourth time, so you are collecting different data statistically, and that data will show some kind of uncertainty. So if we plot the number of instances or number of measurements in which each value is measured, and it will give you a histogram. And once you have a histogram, this histogram or this distribution will have some kind of mean value, and there will be some kind of standard deviation. Okay, so then once it has a mean value and has a standard deviation, then the value of the measured parameter, it could be momentum or it could be position, can be written as the mean value of the distribution plus minus the standard deviation. This is what we have also seen in the previous lecture, that we are measuring a particular measurement and it has a mean value a and the standard deviation is sigma, then the value of this function is a plus minus sigma. This is what we have seen in the previous lecture. Okay, so it means that the standard deviation is the uncertainty in determining the value of the measured parameter. Okay, so this uncertainty which we have now just discussed, which is related to the standard deviation, is not related to the imperfection of the measurement system, but it is inherent to the association of the wave packet with the particles. In other words, the uncertainty is related to the wave particle duality. So before we go and discuss further more about the statistical nature, let's have a quiz, and this is the question that you need to answer. So estimate the minimum kinetic energy of a non-relativistic electron which is confined in a region of width L is equal to 0.1 nanometer. Okay, so let's develop a concept and using a very simple idea. So let's first understand what is the distribution. So if a random variable a takes values ranging from a1 to an, then the average of this random variable is estimated in this way, which you know very well. 1 over n is the number of measurement that you have done, and you sum over all the measurement and then you take this value. Okay, once you have estimated the average value, then you can also estimate the standard deviation, where the standard deviation is given by this simple formula. Okay, we will simplify in a next slide, or we will rewrite into different form. So this is what it is written. Now what you could do, simply you can expand this square. So what you will get ai square plus a average square, and then you will get two more terms. Okay, so then it is easy to establish that this quantity and this quantity is the same quantity, where the standard deviation is written as a square average minus a average square, and then you take the square root. Okay, where this quantity is given into this one, which I have shown you here. Okay, so let's come first understand Gaussian distribution, or what I would call as a normal distribution. Okay, and this particular curve, or the shape of this curve, is known as a well curve. So we have seen in the previous lecture that a Gaussian function or Gaussian distribution has this specific mathematical form, where this part is a normalization constant. I will show you in the next slide that how to estimate this value, and then this e to the power minus a minus mu whole square divided by sigma square is a very specific form of the Gaussian function. Okay, what it means that this, if you take the average value of this function, which is denoted by this mu, or which is value mu, so whatever is with this minus is always average value, and this is your standard deviation delta a is sigma here. So if you plot your first curve with mu is equal to 0, so uh, it means that there is no average, and you could think in other way that this function is situated at a is equal to 0. Okay, so that's why it is 0, and then you can choose different values of sigma. So once you have chosen let's say 0.2, the value of sigma square, the function looks like in a blue curve, and once you increase the value of your sigma square, you see that your curve will start broadening, and if you keep increasing, this is the yellow which is more broad. Now if you take the value of mu is equal to -2 instead of 0, you see that your curve is shifted and now it is peaked at -2. So the value which is coming with a here with the minus sign also shows that at what point or what value the curve is peaked, which is also equal to the average value of this variable a here. Okay, so now we could define that a probability distribution function is normalized if this fulfills this particular condition. So let's see how this look like. So let me write down a distribution function. A is equal to f of x is equal to a times this exponential minus this square, which is a Gaussian in nature, and now estimate what is the value of a so that this function is normalized. So we can substitute this value of f of x here. Okay, so let's substitute it here. Okay, now a is a constant, it is not dependent on x. Now what I can also do that x minus mu I can assume as a y, so change a variable. Okay, so this is what I have written, and the integral of this particular Gaussian function has a very specific value. Okay, so this is the value of your Gaussian integral, and once you use this identity for this integral, it is straightforward to show that the value of a comes out to be this, and once you substitute the value of a from here to here, then you can write down your function in this form which we have seen in the previous slide, and then you can easily say that the function is normalized. So this is the definition of a normalization of a distribution function or probability distribution function. Okay, so this is the function what we have seen in the previous slide, and now let's ask what is the maximum value of this function. So we can substitute the value of x is equal to 0. That's what we have seen. The curve is maximum at where it is peaked. So this is peaked at x is equal to 0. So we can substitute x is equal to 0 here. So we can know what is the maximum value. So the maximum value come out to be this constant. Okay, so here is the distribution, and now we have to define what is HWHM. So HWHM is defined as half width at half maxima. So what it means that at what value of x the function attains its half value with respect to its maximum. So what is the value of x where f of x becomes f naught, f of 0 divided by 2. We know f of 0. So now we can substitute that f of 0 is equal to 2, and then you can know this x at this value of x, the function attains half width at half maxima. Okay, so this is what we have written. This is the value of your HWHM, and now we can also define FWHM, which is full width at half maxima, which is the double of this half, which is 2 times of this one. Then it is clear that your this HW or FW is proportional to sigma. Okay, and then this sigma is also related to your standard deviation. So this width of this function or this Gaussian distribution is proportional to sigma. Okay, so now let's recall our conversation about Fourier transform or Fourier integral, which we have discussed in the previous class, and say what is the Fourier transform of this Gaussian function. We know the answer. The Fourier transform of a Gaussian function is a Gaussian function, but what we are going to discuss now is that how the Fourier transform a Gaussian function in K space looks like with respect to the X space, or in momentum space with respect to the position space. Okay, so this is the definition of your Fourier transform. We know the value of f of x, so we can substitute the value of f of x here. Okay, so this is what. Now what I do, I can collect all the exponents. So what I got, minus x square over 2 sigma square minus ikx. Okay, So what I can do, I can make a perfect square. So I can make a perfect square by adding and subtracting sub quantities. So you are master of doing this thing. So you can verify that once you want to make a perfect square. So this is the perfect square you will get, and you get this additional term. And now this is a function which is a big function of x. So to just simplify the things a bit, I can do a substitution of variable, and I can call this value as a y. Okay, and then I substitute everything back. So what I got here uh, is this one. So I got square root of 2 sigma here. This is my x or y independent, so I have taken out, and this is the function I got. And I know the value of this integral, which we have used when we wanted to estimate the normalization constant of this distribution function. So this is the answer that you can get. So it will come out as a square root of pi, the value of this integral. Okay, because alpha is 1 here, so alpha is 1, so only square root of pi comes out. So it shows that if you take a Gaussian function, you perform a Fourier transform, you will get a Gaussian function, and here is some different prefactor you will get it. Okay, so this is what I have said it. But the important notice is that the width of this Gaussian function is something here, and the width of this Gaussian function is something here. So that's what we are going to understand. Okay, so this is what is given here, and this sigma is same. So now let me put a subscript here as a sigma x square. Okay, so if once I put a sigma x square here, then I have to put also the sigma x square here. So this is what I have done here. So I have just substituted or introduced a subscript in the sigma because it's both sigmas are same. Okay, now I also know from the reciprocity relation that sigma x and sigma k is equal to 1. Okay, that is the one that is given by the Fourier transform, or the reciprocity relation is coming from the Fourier transform, or vice versa, whatever way you would like to think. So it means that I can write down my sigma x is equal to 1 over sigma k, and once I do here 1 over sigma k, then I can get this value. Okay? So it shows that Fourier transform of a Gaussian function is a Gaussian function, but with different sigma's value. And let's understand how they are going to affect each other. So here is the standard deviation is sigma x, and here is the standard deviation is sigma k. Okay, so let's say this is a Gaussian function in a solid dark black line, and if you perform a Fourier transform, it will come out to be this one. So it means that if this is a broad function, after performing a Fourier transform, it will shrink. Okay, that's what the reciprocity relation says, that if something is bigger, the other quantity has to compensate so that the product remains 1. Or if this is a Gaussian function which is shown by the light gray color, then its Fourier transform will be broad Gaussian function. Okay. Now let's come to another concept which is called as a Gaussian wave packet. Okay, we have seen the notion of the wave packet in earlier classes. Here we are going to come or discuss a specific example of a wave packet which is of the Gaussian in nature, or has a mathematical form of Gaussian type. So here I have written my g of k. So it is clear that this wave packet has a variance sigma k square, okay, or the standard deviation sigma k, and it is situated at a value k0. Okay, now if I perform a Fourier transform of this g of k and try to get f of x, so here you could do it by yourself, and this is the value you will get it here. Okay, so you see here you have same normalization value or some constant a, then you get the square root of 2 pi, that's what you have seen in the previous time, then you get sigma k, then you get some additional part e to the power I k0x, because this function is situated at k0, so that's why you will get this e to the power I k0x, and then you get a Gaussian. Okay, so it's clear that because of this function, this f of x is complex in nature. Okay, and if I take the real value of this one, then it will become cosine k0x. This is the same what you have seen in the previous lecture, where we have taken a constant function, and when we have performed the Fourier transform, we have got this complex quantity times sine square kind of function. Okay, and this, when we have plotted the real value of this that time in the previous class, we have got the cosine. So this is the first oscillating part. Okay, and this is what is given the envelope. So you see this function is still as a Gaussian. Okay, and the oscillations is given by this oscillatory part, which is in the real space, and this is in the momentum space. Okay, so here are a few pictorial examples. So here, if you take f of k and if you perform a Fourier transform, it has a lot of oscillations. Okay, now if you, with respect to this function, if you brought the function, its a Fourier transform will shrink with respect to this one. However, if you shrink a function with respect to this one, so here this is the width has been reduced with respect to this function, so its a Fourier transform is broadened with respect to this one. So this is how the, let's say, the reciprocity relation is come into play when you are doing let's say the Fourier transform of a Gaussian wave packet. Okay, so this is what we have written here, and this is what we have written here, and both have a different variance, and this is the relation what we have seen in the previous class, previous slides. So now what you could do, you could multiply this sigma x square into sigma k square is equal to 1. That's what it is giving you, and we know that these variants are related to the standard deviation, which is your delta x and delta k. So this is what I have written down here, delta x and delta k, and now I can convert this delta k into delta p. So once I convert, I will get h cross. So for a Gaussian wave packet or for a wave packet, this is the uncertainty relation that you get it. Okay, and not h cross by 2. This is something that you have to keep in mind. Okay, so when you have a wave packet, this is the uncertainty relation comes, and when you have a distribution function, then you get h cross by 2, which we are going to see in a moment. Okay, so let's again recall the meaning of uncertainty. So let's consider a large number of measurements of positions x. So let's say that this measurement has a mean value x bar, and now if you want to calculate the mean value of any power of x, so here we are calculating the mean value of x to the power n, which is defined as, this is a definition in general. So if you want to calculate the mean value of x to the power n, so you multiply this x to the power n by the distribution function, integrate over entire space, and we don't know whether this distribution function is normalized or not normalized, so we have to divide by integration of this distribution function, so that this quantity does not get affected by the fact that this distribution function is normalized or not normalized. Okay, so now we can estimate the variance. We have shown that this variance is defined in this following fashion. So if you take everything carefully, then we can write down this is what we have seen, that the variance square is denoted by average of x square minus average of x square. Okay, so this is the quantity that we have got it. Okay, and sigma is uncertainty, and variance is given by the sigma square. Okay, and this sigma is the standard deviation also. Okay, so now with the all the definitions that we have just now seen, let's estimate or consider a Gaussian probability distribution function. So here now we are considering distribution function of a Gaussian shape and not a Gaussian wave packet. Okay, so this is the difference that we have. So this is a distribution function. Okay, it has a mean value mu, and it has a standard deviation sigma. Okay, so that's what I have said it. So now you can estimate that your x square will be mu square plus sigma square, and these are some standard relation that you need to use. So now I can calculate my variance, which is given here is sigma square here. I know this, all these value. Okay, so my standard deviation sigma is this one, and we have seen that the distribution function, Gaussian distribution function, is peaked at mu, because here you have x minus mu, and if you go with this 34%, this is what you call as a full width of maxima, which is mu plus minus sigma, and if you keep going to some other values, it's plus minus. So it gives you the what is called the range of distributions or confident range of your distribution function. Okay, so now here is another important definition. So let's say you have some quantity O and you want to compute the average of this quantity with respect to a distribution function. So here is defined as the average of this O as psi star O psi divided by the normalization of this thing. Okay, so now this is my G of K. Okay, in terms of my let's say the uh, kind of thing that you have seen in the case of wave packet, and this was its Fourier transform. Okay, so now what we are going to do, we are going to compute delta x and delta k. So when we are going to compute delta x, we will use this distribution function, and when we will compute delta k, we will use this distribution function. Okay, or this part of the function in this one. Okay, so that's what I'm going to do. So we can estimate this quantity. So first we will compute average of x. So when you put the average of x, you know all the values, you know how to perform this integral. You can verify by yourself that it turns out to be the 0, and when you want to compute the average of x square, okay, then it will come out to be 1 over sigma k square. Okay, by using this definition. Now we can do the same thing. We can compute delta of k square. Okay, so this is what we have got it. So remember, this we are going to use in the next slide. So now I'm going to compute delta of k square. So by using the same relation, okay, delta of k square you can estimate by yourself or whatever way you want to estimate. It will give you this value. So sigma k square by 2. So now I have got delta k square. I have also got delta x square. So I got delta k. Also you can take a square root. I can get a delta x here from the previous slide. Now if I multiply the 2, okay, what I will get 1 over h. And now if I convert this delta k into delta p, so it is clear that my delta x times delta p is equal to h cross over 2. Okay? So when we have a Gaussian wave packet and when we want to estimate the product of this uncertainty relation, then we are getting h cross over 2 and not h cross. Okay, sorry, when we have a Gaussian function, Gaussian distribution function, and when we wanted to estimate the delta x times delta p, then we are getting h cross over 2, whereas in the case of our what you say um, Gaussian wave packet, we were getting the h cross. Okay, so this is what we have seen. Okay, so let's summarize. So for the Gaussian wave packet, what we have seen that this is related to the delta x delta px. Okay, and now this quantity is different than what we have seen in the case of the measurement. So when we estimate the uncertainties in measurements using relevant distribution functions or the wave function, we obtain this quantity. Okay, so this is Heisenberg uncertainty principle, whereas in the case of the Gaussian wave packet, this product is related to the variances of g of k and f of x. Okay, so before I end today's lecture, let me provide the recommended readings. Okay, so if you would like to read more about Heisenberg uncertainty principle, please go to section 5.5 of this particular book. Thank you very much and see you in the next class.